In this video, I'm going to show you how to calculate and plot true stress and strain, assuming you already have engineering stress and strain. So why would we want to do this? Well, one of the biggest reasons is that if we want to get information about strain hardening of a metal, we need to have true stress and true strain. All right. So let's start with what true stress and true strain are. So here are our definitions for true strain and true stress. So let's start with the strain. So strain is always the epsilon, and then we have the T subscript, and this is equal to natural log of Li over L naught. So let me just go over some basic things here for these equations. So to start with, if you see the subscript T, this indicates a true stress or true strain. So T is always for true. If you see the subscript I, like you do up here, this is always indicative of instantaneous. So what is the actual length or other measurement at a given point in time? And the naught or the 0 or an O, this is indicative of original. So what are the dimensions, say length, at the beginning of the test? So that's what we'll use for all these. So if we go through this equation for strain, again, we have true strain. Again, epsilon is always strain, T true. So true strain is the natural log of the instantaneous length over the original length. And both of these are going to be from the gauge, so the reduced section of the tensile sample. So now if we move over to strain, we have the same expression. So stress is sigma. We have a subscript T for true, so true stress. And this is equal to the force over area. And this is the instantaneous cross-sectional area. So again, we're using instantaneous. And so if you've already plotted your engineering stress strain or already calculated these terms, the big thing you'll notice the differences between engineering and true are these instantaneous values here and here. So true stress and true strain rely on instantaneous values as opposed to original values. All right, so let's say that we want to plot a true stress, true strain. Again, instantaneous, this can be difficult because this implies that we're measuring each time point. However, there is going to be a shortcut here, and that is the fact that we can convert from engineering to true strain and stress. So there are conversions for engineering to true strain and stress. And so that's what we're going to do in this example to determine the true strain and true stress. So here is our conversion for true strain, and that is equal to the natural log of 1 plus epsilon. And here you don't see the subscript T, and so this is the engineering strain. So we take the engineering strain, add 1 inside the natural log, and we get the true strain. So this is a conversion we can do to get true strain. We can also do a similar operation for engineering stress to true stress. So again, here's our true stress equal to the engineering stress multiplied by 1 plus the engineering strain. So these are our two conversions for this operation. And so we have to make a caveat here. So we can convert from engineering to true using these expressions, but the big caveat is that this is only valid up until the point of necking of the sample. So that is a condition of these expressions. They essentially break down once necking or once the cross-sectional area becomes heterogeneous, so whereas there's the necking and then the rest of the bar, these become invalid. And so if you really, 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 really need the true stress and true strain for the entire curve, what you would have to do is manually measure the cross-sectional dimensions of the necked region. So that would imply that your in the machine with calipers while the test is going, while the necking is occurring, and you're measuring with calipers that necked region. And so then you would manually input these instantaneous dimensions into the equations as you do that. I've done this once as an undergrad as part of an experiment to kind of show this, but for the most part, this isn't done. Maybe if you had a better optical system, you could do this, but for the most part, we're going to rely on just anything before necking to convert. All right, so with that, what we're going to do is we're going to switch over to the Excel sheet, and I'm going to go through an example of going from engineering stress and strain to true stress and true strain. All right, I've switched over to Microsoft Excel. I'm running on a Mac, so yours might appear a little differently if you're using a PC, but I'm going to walk you through how to go from engineering to true stress and strain for a metallic sample. So just a couple notes about the sample we're going to be looking at. This is a 4140 steel sample. It's been quenched and then tempered at 200 degrees Celsius. This is the output file from our Instron. I have the thickness, width, so it's a rectangular cross section, and the gauge length all up here manually. And the time, displacement, force, and tensile strain are all given to us from the machine. And so I've already gone through how to calculate the engineering strain and stress. So if you don't remember that, please see the other video that I'll link to in the caption. So if you need that, go back to that video first. We're going to assume that you have the engineering stress and strain. And I've actually got that over here plotted. So this is what this sample looks like. A couple notes about this sample. You might notice this little drop that happens. This is an artifact of our testing. We use an extensometer, which measures the elastic region more accurately. And when we take that extensometer off to avoid it breaking, it leaves this little drop in stress. And so that's just an artifact of our testing. If you want to see more about why we use an extensometer, I'll also have a link to that video that you can look at. So this is our engineering stress strain curve from the data over here. I've already plotted these two columns that you see. And so now we're going to go through and do the true strain, and we're going to do the true stress. So true strain is going to have the same units, millimeters over millimeters, which is unitless. Stress is going to have the same megapascal units that are engineering stress, and Excel doesn't like me, so it always uncapitalizes my megapascal here, so I have to convert that. And so let's go through our expressions again. So for true strain, we had that this is going to be equal to the natural log of 1 plus the engineering strain. So I'm going to use F7 for this. So that is our expression for true strain for this sample. And I'm going to just click on the square down here to extend this to the bottom. All right. So then for true stress, I'm going to take the engineering stress multiplied by, it doesn't like that, so I'm going to go back and do 1 plus engineering strain. So that looks correct for this one as well. So again, I'm going to extend this to the bottom. All right, so that's all we had to do. That now has calculated true stress and true strain for all of our data points that you can see here. And so I'm going to add this to the plot so we can see how it looks. So I'll call this true. I'll add my X, extend it to the bottom, do the same for the Y. And there's my true. So I'll add this and we'll see what we get. All right. So you'll notice that if we, let me format this so you can see what we're doing here a little bit better. I'll choose this quick format down here. Okay, so you can see the labels on this. So this is strain. This is stress. And then we have true. Sorry, sorry about that. All right, so the blue is our engineering, and the orange is our true. I did make a caveat in the slides to note that true stress, true strain are conversions that we use here and here were only valid up till necking. And so necking is when the reduced section necks and becomes thinner than the rest of the sample. And so from the graph, we can always get that from the top. So where it reaches a maximum. That is known as the tensile strength, but that also indicates the start of necking. So that means that this is actually going to be really easy to find. So what I can do is I'll just do a simple max formula in Excel. And I'll basically just add all of the possible, I want to do this for engineering stress. So I'll do this for all possible stress values. And then I'll go back up to the top. And I'll see that the maximum here is 2078 approximately. And so that corresponds to the tensile strength, which is great. We could just write that down as our ultimate tensile strength or tensile strength. But what that allows us to do is I'm going to note this 2077.74. And, in this example, I'm just going to kind of roughly scroll through this to do this. There's more sophisticated ways to do this, but just for this example, I'll do that up here. I already forgot the number. So 2077.74. All right. So I'm just scrolling until I find that value. All right. It looks like it's right here. And it doesn't have to be perfect, but that looks like roughly the same value. And so what I can do, because I don't want to represent anything past necking, what I can do is I can come over here to H and I. These are our true strain and true stress. And I can just take these two, scroll to the bottom, and just simply delete. All right. And then if I go back, hopefully this updates. Yes, it updates. And so you can see here that now it took basically all the data up to that maximum, deleted the rest because those equations aren't valid. And so we have plotted the true stress, true strain from the engineering. So this is just one example to do this. Stay tuned for a follow-up video where we're going to use this true stress and true strain data to actually go through and fit the plastic region and get the parameters for strain hardening so we can compare samples depending on their strain hardening. So stay tuned for a follow-up video on that.